Здравствуйте.
Добрый день. Сейчас мы всех дождемся. Так, между тем, я вспомнила, что я вас не добавила в группу. Я тут группу сделала, потому что я поняла, что э, надо покидать. Вот, теперь вас добавила в группу. Okay, and we're going to talk English today. Sorry, because an English speaker. So not everything is possible in Russian. We're waiting for as 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 usual. Um, my main student is missing yet. I mean, everyone came, but I mean, we're waiting for Win today. Okay, guys, I actually created a group for formal semantics documents. Okay, I guess here's Win. Tamar, I created a group in Telegram. I'll give you
Well,
the link.
unfortunately, Telegram does not work with my phone number still. I
Oh,
had a problem with it and it still doesn't work. That's fine. It's
oh,
okay.
I'll send you the documents, I
All
guess.
right, thank you.
Right. Um, so guys, sorry, but today we're speaking English because not everyone speaks Russian here. And we were discussing several things. Tamara, I'm going to send you the documents I shared in the group. I think should be that. Yeah. So, in Telegram, you can see the textbook, the really short, brief explanation of what we discussed last week ago, and a brief explanation of what square of a position is. I'd ask you to look at those documents to follow us. Okay? Yeah. Can everyone see the files?
Yep.
Yeah, good. Win, as you suggested, we're starting with
Yeah, rundown of the concepts that we went through in the last lesson.
exactly. So core topics in semantics. We've got three key semantics relations. Yeah, we've got entailment, we've got presupposition, and we've got implicature. Right? Win, can you explain the concept of entailment?
Okay. I mean, it's pretty well explained in the semantics intro handout. It says entailment is when one sentence must follow from another. Yeah, like if the first is true, the second cannot be false. Yeah.
Yeah. And Seva, can you explain the idea of presupposition?
It's a sentence. It's um, it's a statement that is assumed when asking a question. Like the question, have you stopped drinking cognac every morning? Supposes assumes that a ski used to drink it every morning.
Yeah, and we've got implicature when.
Okay. Implicature is something that is inferred from context, but if it's contradicted in like later sentences, that doesn't mean that the sentence was false.
Right. Okay, and the difference between the entailment and the implicature?
Okay, well, entailment is to when, you know, if the first is true, the second cannot be false. And the implicature is like it can go either way. It's you assume one thing when you read a sentence, but then, if that's not actually the case, that doesn't, it doesn't really change much except, oh, I guess that's not the case.
Okay. And the difference between the implicature and presupposition?
I mean, those are like kind of totally different. Okay, no, they aren't. Presupposition is when, you say a sentence, and for that sentence to make sense, you have to kind of assume a thing that, like, an initial thing that's kind of based on. Like in the example here, Sue stopped smoking presupposes that Sue used to smoke, because it would be weird and would make no sense to say that about someone who has never smoked. So
Yeah, but what's the difference from the implicature? Because implicature presupposes some things as well.
does it? It's not really. I mean, like it's socially you can infer some things, but it's like it's just that it doesn't necessarily. You
I
can't
mean,
assume it
we've got
necessarily.
a
It's not
certain
necessarily true.
we've got a certain strict thing that helps us to tell the presupposition from other forms of semantic relations. What is important for presupposition? Okay, I mean, it holds with the negation test, right? You remember that? Sue stopped smoking or Sue didn't stop smoking, we still assume
Oh yeah.
she once smoked. Okay?
Yeah, so if the negation of a sentence leads to the same presupposition and presupposition.
Yeah. This is it. So, next thing, square of a position. Yeah, I think I'll share the textbook, and you have this summary. Okay, this thing is called a square, the square of a position. Okay? We have certain How do we say it in English?
Statements.
Statements, thank you. Like every S is a P, where every is affirmative universal and some is affirmative existential, if I remember it correctly. Every S is not AP, is affirmative, is a negative universal, and some S is not P, is negative existential. Okay? And we were discussing semantic relations like where was it? Contradiction, equivalence, then contradiction,
Contradictory and contrary statements.
contradictory and contrary, yes. Yeah, contradictory and contrary opposition. And can we explain the difference? Where was it? Okay, I forgot it. So, contradictory and contrary, what's the difference?
I mean, the test is that contrary is a case where there is a case where it is possible that both of those are false. Like it is possible that there's a third group that's not either of those. And contradictory statement is when both of the statements cover every case possible. That's the test.
This
for that.
thing should be difficult, right? Do you understand that? Is it clear? Not so clear. Okay, let's well, actually, S is a sailor, P is a pirate. Every sailor is a pirate. Every sailor is not a pirate. Some sailor is a pirate. Some sailor is not a pirate. This is what stands behind these examples, right? And oh, one moment. One moment, sorry. Okay. One moment, I'll just switch the windows a bit to
Right.
yeah.
So are we going over what contrary and contradictory statements are?
Yes, and their
Okay. I mean,
relationship to the square
yes.
position.
So if you scroll down or scroll up, excuse me, a couple pages higher to page 33, there is something that explains it.
Yeah, but can we explain?
Can we? Okay.
So we have a
I mean, I
semantic
feel like they explain it
relation,
pretty well.
which is a contradiction. This means that two statements cannot both be true and cannot both be false.
AKA mutually inconsistent or incompatible.
For example, all cats are animals. Some cats are not animals. Yeah, cannot both be true cannot both be false. Yeah, so one of them is always true and one of them is always false. Okay? I'm going to write it this way. Yeah, all cats are animals. If it's true, then the statement some cats are not animals is false. Always. Okay? And if some cats are not animals is true under any circumstances, then all cats are animals is false. Okay?
Okay.
This is contradiction. Only one can be true, and one is always true, one is always false.
As you can see, that goes diagonally on the diagram from every S is a P to some S is not a P.
So this horizontal line is contradiction, right, Win?
No, that's I believe.
Every S is AP, every S is not AP.
No, isn't that contrary though? Contradiction is
Some
diagonal.
S is not AP.
Hmm?
This one
Yes,
is
some S.
Yes,
Yes, diagonal.
between A and O.
Yeah, this one is a contradiction. Right. Okay. And we've got semantic relations, which is contrary. Yeah. All cats are friendly. No cats are friendly. They cannot both be true, but one of them, but they can both be false. Okay? For example, okay, let's go with that. Sorry. All cats are friendly. Oh, sorry. Friendly. All cats are not friendly. They cannot both be true. Only one of them can be true. But they can both be false if all cats are not I mean, if
some cats are friendly but
cats,
some aren't.
yeah, are friendly and some cats are not friendly. Yeah. Now, Win, which is contrary?
Sideways, like horizontally.
This one. Okay.
No, that's vertical.
All right. This one.
Yes.
Yeah. So let's say red or contrary. Always.
And contradictory, the line between A and O?
It's any diagonal line.
Contradictory or diagonal.
Mm-hmm.
Okay. So this was actually about terms. So and we were going to start with chapter 2 today about sets, relations, and functions. Okay. So, M you remember that we have these examples like every sailor is a pirate, some sailor is a pirate, no sailor is a pirate, some sailor is not a pirate. Yeah, these were the corners of our square of oppositions. So, we have a certain sets, a set of sailors, which includes all the sailors in the world. And we have a set of pirates, all the pirates in the world. Now they can intersect. If the set of pirates include the set of sailors, then we have every sailor is a pirate. So universal means that it's inclusion of sets, one into another. Yeah, all the sailors are inside the set of pirates, of all the
AKA a
pirates.
subset.
Yeah, sailors is a subset of pirates. Now, sets do not intersect. Then no sailor is a pirate, right? No sailor is a pirate. Neither set is a subset of another set. Okay, they do not intersect. Okay, and this is full negation. Right. Now, if the sets intersect, we get this: some sailor is a pirate. And the sentence is true only for this intersection marked X. Okay? When sailors are pirates, some sailor is a pirate. And if we take the other part of the set of sailors, which does not intersect with pirates, then we get a partial negation. Some sailor is not a pirate. Okay? And as you can see, this is actually our corners of the square of positions, only expressed with Euler's diagrams.
If you really think about it, I is a subset of A and O is a subset of E.
Okay, yeah, because this is a universal approach and this is existential approach. Yeah, I should remind you that we have these logical operations. Now Win helped me with it again. Okay, this one is universal and this one is existential, right?
I think the bottom one is any and the top one is there exists
That's what
A.
we actually
Tell me to go on Wikipedia and look up logic symbols again. Okay.
That's the thing I always fail at.
All right.
I mean,
So, yes, the upside down A is given any, for all, for every, for each, for any.
so
And then
every,
the other one is there exists, aka for some.
yeah. So this is every, and this is some. We're going to use these things. So I guess, yeah, actually, Ola can help us with logics and math, I guess. Yeah, right? I mean, you probably know about it more than I do. Okay.
Not hard.
Yeah. Not hard for logical people like yourselves, but not for intuitive like myself. Right. Okay. So we're thinking about this thing as a set. For example, this X is a set of sailors that are pirates. And this X is a set of sailors that are not pirates. And we can explain the world around us as as sets. I mean, all the things and people in the world can be explained as sets of something. Okay, and that is called set theory. Yeah. So every set's got an elements or members. And here we use this sign that means this element
Belongs to
belongs
set.
to this set. Yes. Right.
We tricked you, everyone. This is actually intro to grade 10 math.
Yeah. So and we've got these things something like sets can be equal and your math people, yeah, and set A can be included in B and B can be included in A, right? Win, can you explain these signs for people like me, non-mathematical?
Okay, sure. I'm just opening mathsisfun.com right now. I don't remember this off the top of my head. So the first one there, that means that A is a subset of B, aka
A
every element
is a
every element
subset
of
B.
yes, aka
Yeah.
every element of A is in B. And then
here is B is subset of A.
yeah, it's the other way around, basically.
So subset is from that side where it's closed, right?
Yeah, basically.
More or less. Right. Okay. And
Bear in mind, by the way, those are non-proper subset slash superset symbols, aka both of those sets could have exactly the same values.
The same what?
Values, like stuff in it.
Okay, sets can be indefinite. For example, a set of girls includes
No, a set of girls is actually very finite. A set of even numbers, let's say, right there.
what's okay, the set of girls is finite, and can you give me another example of a infinite?
I did just say you can look at the page right there. It did
Yeah, I
even numbers.
understand that numbers,
Okay,
yes,
fine.
but
Prime
anything else?
numbers. What do you want? Like,
What else can be? Okay. So anyone can come with another example of infinite set?
All possible strings containing 0 and 1. It's an infinite set.
Yeah, thank you. Right. Okay, about concrete and abstract elements, I think we all understand what this means, right? And even some members of a set is unknown to us, it still has a right to exist. Yeah, this is about known or unknown. I mean, yeah, the set of Roman emperors is well defined. Or if you're a Roman emperor, you belong to the set. If not, you're not. And doesn't matter if anyone knows you. Right. Then we come to a term of a predicate. So we have variables here. Yeah. And as in programming, we use certain variables. It's only that semanticists tend to choose like N or M letters for those variables to describe sets of integers. Or elements.
I mean, that's just math stuff, I think.
Yeah. So we can describe a statement as this thing and this logical actual thing, and we read it as the set of elements n that belong to integers. Yeah,
integers.
Thank you. And below 0, right? But this
basically
is
negative numbers.
Can you read it correctly?
The set of all n such that n is an integer and n is less than 0.
Let's repeat it for non mathematicians like myself. So, can you say?
Okay. I don't know. If you take n as like a
You said it
placeholder,
completely correct. Just can you repeat it slowly?
Oh, just say it again. Okay. The set of all n such that n is an integer and is also less than 0.
The set of n's such as n is an integer and below 0, right?
Yeah,
Yeah,
such that.
such that. Okay. So, we know that the set can be empty if it contains no elements, and it can.
Cardinality is basically just how much stuff is in the set.
So, cardinality is the number of elements in the set. Is that correct?
Yes.
Yes, good.
It's the number of elements it contains. Its length, basically.
Okay. Right. And there might be a set with only one element, and we call it a singleton set. Is this math as well?
I don't know, I guess.
Okay. And some sets can contain other sets. Actually, we saw it on sailors and pirates, right? Probably.
Yes.
But yeah, so we have a set of 2 elements, and the second element is a subset. And an empty set, again, can be an element of a set, can be an element of a set, yeah.
Nested arrays.
Right. The only kinds of things that cannot be members of a given set are certain other sets. Can you explain that? This Russell's paradox.
There cannot be a set of all sets that are Yeah, okay. I mean, do you want me to explain Russell's paradox
Yes.
specifically? Okay. I mean, I don't know if you've heard the question, does a set of all sets contain itself? And that's basically the paradox, because if it's a set of all sets, you know, yeah, there cannot be a set of all sets that are not members of themselves, since that set could neither contain nor fail to contain itself. That's the paradox.
Actually, I'm really stuck there, but I suggest to think for those who are stuck as myself here, let's think about the Russell's paradox at home.
I mean, it's very easy to extrapolate from just, the question, does a set of all sets contain itself? That's it. That's all you have to think about.
Okay. Yeah. My brain is broken. Confess. All right. So, and those sets have relations, right? A is a subset of B.
Yes, written with that symbol. You didn't even have to have me explain it.
Yeah, I guess we discussed that. A set AB is a subset of ABC. Yeah, but not otherwise. Not in the other direction. Empty set is a subset of every set, but not an element. It can be an element of some set, but not an element of every set. Yeah, I mean, empty set can be found in any set. And any set contains an emptiness, something like that. So is the empty set a subset of, and you like a set of pirates? Yes. Is empty set a subset of a set of sailors? Yes. Of a set of girls? Yes. I mean, doesn't matter which set, an emptiness contains in every set. Okay, so now we come to a proper subset. Which emerges because we need to avoid confusion. Yeah, so a proper subset is written this way without the equal sign. And this is a proper subset. A is a proper subset of B. Yeah, this means that A is a subset of B and A is not equal to B. All right. Does everyone follow?
It's a little bit weird that sign for subset is more complicated than sign for proper subset, despite despite it being less commonly used.
It's like the less than or equal sign. It's just it's like half of an equals.
But
It can
you
also be
use
the same.
less sign probably more often than less and equal, but proper subsets are used less often than just subsets in semantics.
I mean, some people actually use the sign for proper subsets for like all subsets, which is not entirely correct, but it's just easier, so people do this.
But since proper subsets are so rarely seen, nobody cares about that usage.
Well, yes.
All right. So now we come to a concept of power set. Queen, can you explain that?
Okay, let's see. So I guess a power set of S being an arbitrary set that you have. I guess the power set of S is just all of the subsets of S possible, I guess. I don't know, that's what it says, man.
So the power set includes all possible subsets in of a set, right? So set of A, B includes empty set a singleton set including a singleton set including B, and a set AB. Yeah? This is called a power set. Now, superset win.
A superset is just the opposite of a subset. It's the thing that contains the subset.
So we just reverse the sign.
Yeah, basically.
Yeah.
Like I explained it earlier.
Okay. And the proper subset, we take away the equal sign from this reversed sign, right? And
Yeah.
yeah, and we have this disjoin thing.
Disjoint.
I mean, if they do not intersect, right?
Yeah, that's what it says.
Then they are disjoint.
Yeah.
Okay. So if an intersection of A and B gives an empty set, in fact, right? Is that correct?
Two sets with an empty intersection are disjoint. Yeah.
Yeah. Right. Okay. And we can have operations on sets. Now actually what we should do here is to understand the difference between relations and operations. And I invite everyone to look through this part and try to explain the difference between operations and relations.
Can I just explain it?
Yeah.
Okay, so a relation between sets is you describe what those sets, like how they relate to each other. Operations is you do something to the sets to like make a new set or whatever. Yeah.
And the principal operations are intersection, union, and complement. Let's look at that. Intersection is if
it's the stuff in the middle of the diagram that's in both.
Like some sailors are pirates, right? Is that correct?
Yes, the ones that are both sailors and pirates.
And that we will use this this sign, right? So some sailors, some A, are B. No.
Wait, yeah, I don't know.
I guess not.
No, that's what it says. Why are you asking me, man? Like,
some sailors are pirates.
Yes.
Yeah.
Think of it as like connecting, I guess, two things with the like wires. Do you know those like breadboards that people have sometimes where you can like connect stuff with wires and stuff? It's like that kind of.
Okay.
I don't know how many people understand what I'm talking about, but whatever.
Guys, I suggest if anything looks confusing, we discuss, okay? I mean, it's not just a dialogue of Win and myself with the inclusions of Seva and Ola. And by the way, I'm grateful for Seva and Ola speaking. Okay, union How do we explain it with sailors and pirates? Can we explain it?
It's just the stuff that is in either one of those or in both. Just all of the stuff that belongs to either category or
I mean, everyone who either sailor or a pirate
both, yeah.
or both. Yeah, and we
Yeah.
use this sign
Yeah.
to do
Think of it
union.
like, imagine like a basket that you're just like putting all of the stuff in. I don't know.
all sailors and all pirates and all
Yeah.
sailors that are pirates. Okay.
Sailor pirate soup.
Yeah. Right. And we have an examples. Let's check. Okay. D is a set of doctors and L is a set of lawyers. And now we've got this sentence. Anna is a doctor or a lawyer? Which one describes this question better? A, B, C, or D?
I think probably someone who is not me should answer that.
Anyone? So, Anna, Anna is an individual, so it's not a subset, right? So she belongs to either D or L. So we but we should choose only one for her. Yeah, guys, help me.
I don't know. I think it only one is not necessarily true.
So you think this one?
I mean, yeah, because the other one is the intersection.
Yeah.
I mean, logical or means that it can be one, it can be another, or it can be both.
Yeah,
That's like
exactly. This is not like XOR or anything.
Okay.
yeah, it's not XOR.
Yeah.
It's not what?
XOR, you know,
XOR is like
exclusive or.
exclusive or, yes.
Yeah, only one of these is true, and you know, gives the output true, and if both are true or both are false, then the output is false. Anyway, yeah, continue.
Okay. Right. Now, again, D is set of doctors, L is set of lawyers, and R is a property of being rich.
Okay.
So every doctor and every lawyer is rich. So as there are other people, not doctors and lawyers, who are rich, then again, we should choose from A or B, right? And as we should, we have this operator and then it's A. Is that correct?
Yes.
No, because that's everyone who is a lawyer and a doctor at the same time. That's the intersection one.
And this is A, right?
A is the intersection one, yeah.
Yeah.
And we need the union one. Because
Yeah.
we also need to include people who are only doctors or only lawyers.
Right. Okay. Then we have set difference. We can subtract one set from another. Yeah, and we get the set of all things that are in A, but not in B. I actually cannot easily apply it to sailors and pirates or doctors and lawyers.
I mean, you kind of can though,
Can you?
because it's just like you have a set of pirates or whatever, and then you just exclude everyone who is also a sailor.
Uh-huh. And then you get all the pirates
That are not sailors
that are not sailors.
somehow, but you know.
Well, maybe they only kill people and they serve as passengers on pirate ships.
No, I think that makes you a sailor probably. But anyway, I don't know, land pirates. Whatever. Let's move on.
Okay.
Internet pirates.
Oh, sure.
Right.
That is pretty good, yeah.
Okay. Now, quantification is a first semantic theory, and we're going to discuss it for English. I mean, it might be different for other languages, language-specific thing. Like again, NP is a noun phrase, and we can put here either sailor pirate, and D is our existential or universal, like, or negation. Every, some, or no. Yeah. And here's a semantic representation of phrases like every sailor is a pirate, every pirate is a sailor. Yeah, some sailors are not pirates. Yeah. Right. Is this notation clear? Do you like anyone needs more time here? Okay. We're moving on. Oh, more math. I'll be dead in the end of this part. Okay. Does everyone understand that you can just open your PDF and yeah, follow us, look in the PDF and not on my Zoom window. Right. Okay, let's say this math goes for homework because I'm not ready to discuss, and we can discuss this sort of exercise next time. Of course, it demands time. Yeah. And so there is a closed set of sentences that can be generated using these trees. Let's try to generate all possible sentences from A. How many are they? Okay, who can we lost Win? Right, we lost Win.
No.
No. No, we lost someone. Lenya, okay. Lenya's gone. Queen, Ola, Tamar, Seva. Who would volunteer to generate all possible sentences that can be represented by this tree? Go on, guys.
I mean, I can.
Go on. How many?
Every sailor is a pirate. Some sailor is a pirate. No sailor is a pirate, and also symmetrical ones where you just switch pirate and sailor, I guess.
So we have 6, right?
Yes.
And what about B?
It's the same stuff. It's just there's a knot in there.
All right. So, can it be just 6, right? No more? Yeah, I think so. Yeah, as we see, you should be correct, as they give us 4 possible sentences and suggest we generate 2 more. Then I think Ola's absolutely correct that it should be 6 sentences generated by this tree. Right. So, sailors and pirates are sets of individuals because we have those 1 sailor, 2 sailors, 3 sailors, 4 sailors, right? This is called sets of individuals. Yeah. And I mean, set of individuals is certainly a term. I remember that. And again, I think you understand that better than me. We repeat here that S is subset, sailors is a subset of pirates, right? And intersection between sailors and pirates is not empty. Yeah. And then an individual can denote a set. Yeah, which, correct me if I'm not right, to denote a set is to choose the set. For example,
No, I think it just like I guess. I don't know.
Look, if NP denotes set X,
And, yeah, it just means like if NP I guess stands for set X, I think.
look, pick out
I guess.
means denote.
Sure.
Right. So, we need to understand, if anyone understand that already, come up with it, with the explanation. What is it? An individual denotes a set. Yeah, anyone? Ah, got it. We can think of a sailor as an object. Yeah, something we can touch, for example. Yeah, and this is an individual. An atomic entity, a single point in the domain of discourse. And then we have this predicate logic with set, and then we say this sailor is a pirate. And then we sort of denote the sailor with a set of pirates. Okay? So we denote an individual with a set of individuals. For example, Sunny is a cat. We have this individual, Sunny, and it is denoted by the set of all cats. All right? Can anyone say that I explain it clearly? Tamar, you look like I wasn't clear enough.
No, you are clear. It's my brain.
Yeah, I always actually I took 3 courses of formal semantics, and each time my brain just breaks here. But yeah, Win, what do you say? These things are usually easy for you.
What, huh?
Okay, I tried to explain the concept of denotion.
Denotation, I think.
Denotation, thank you. Through this thing. We have an individual like a cat called Sunny. We know this cat. We can see it on Win's
Yes,
pic.
that's my boy.
Yeah. And this cat is an individual. We can touch it, like, yeah, we know this individual. But we say Sunny is a cat. And then we denote this individual using the set of cats. Like Sunny belongs to the set of cats. Yeah, and this is denotation. Am I correct?
Give me a second. Okay. Sounds like it, yeah.
Yeah. So sailors is a set of individuals, but each sailor, each particular sailor is drawn from a domain of individuals. Yeah. And is denoted by the set of sailors. Okay. Right, denotation. And now we come to negation. Some sailor is not a pirate. Yeah. And not a pirate denotes a complement, an additional thing to this set of pirates, which contains all non-pirates. You remember, right, this Euler diagram?
Okay, I feel like the notes is much less complicated than you're making it out to be.
I'm
It
happy for your understanding of
it sounds like it's just like, you know, pirate is the like pirate slash not a pirate slash whatever is what we're using as like the, let's say, variable name, kind of like placeholder when we talk about, specific stuff. Like, let's say it's like word meanings. I don't know, like when you say stick, you know that like stick denotes, a like, thing from a tree that like, etc. You know what a stick is. Yeah, like that's just what it sounds like it is.
Okay. I'll just try to repeat a bit. So we have a set that denotes sailors or pirates. Yeah, and we have a complement to this set that contains all not pirates. And negation denotes this complement to the set of pirates. Okay? Move on. So, if NP denotes set X, then not A and P is, and then we have this X with this mark, which means not not a sailor, more or less. Yeah, if sailor makes a set, not a sailor gives us this X strich. X, how do you say it in English? Win. What do you call this thing in English?
I don't know, like the hyphen.
Hyphen, X hyphen. Right.
Like diffuse, I don't know.
And then we come to semantic rules to handle negated predicates. Yeah, and then some sailor is not a pirate is an intersection between S, set of sailors, and this complement of P, and this complement of P is not empty, which gives us this expression. S intersects with complement of P, which is non-P, and this intersection is not empty. Yeah?
There are things that are S and also not P at the same time. Basically, is what that says.
S and not P. Intersection of S and not P. All right. So now we'll have an exercise. Right, and we actually have only 15 minutes left, so I think we do this exercise and then we'll try a couple of exercises about subsets and elements, and then we finish for today. Okay, we have every sailor is a pirate, which is a corner of the square of opposition. And we have some sailor is a pirate, which is corner I in the square of opposition, and so on. No sailor is a pirate, some sailor is not a pirate. Now, let's try to match them with logical expressions here. Come on, guys. I'm not able to do it without you. Help me. Every sailor is a pirate. How do we express it? Like the set of sailors is included in the set of pirates. Yeah, so which expression is this? Guys, even I see that. I'm sure you can see that as well. Go on, Seva. All right. Tamar, can you see that every sailor is a pirate?
I think it's the 8th one or the 7th one.
I'd say this one because
I really suck at group theory and I confuse everything, the up and down, the this and this, like.
No, it's okay. The thing with three prongs means that like the like thing on the left is like a singular thing that belongs to a group. And the subset symbol means that it's like a set of things that belongs to a group.
yeah.
Okay, so the 7th, I guess.
Because of universal here or existential, we have sets and not an individual. And this is why it's 7 and not 8.
So
Okay.
then I would be 8. Or
If S was like a singular guy that was a pirate, then yes, that would be 8.
8 would be like sailor Tom the sailor, is a pirate.
Yeah, like that specific guy.
Yeah. So, some sailor is a pirate. Will help me?
Mm. Oh, do you want me to tell you what it is?
Yes.
That's
Oh,
six.
okay.
That's
Uh,
the sixth one,
6?
I
some
think.
sailor is a pirate.
It's some. So,
No, so
the set
yeah,
intersection is not is not empty.
Like a
yeah.
subset.
If we have some, then we have intersection. Yeah. So then we have this sign, right?
Mm.
So it's either this, or this.
Is this all what semantics about?
This is what
Yes,
formal semantics is about, specifically.
This
Fun.
is what is formal semantics about. To express
Express language
logically.
in a formal logical way, yeah.
Yeah,
That's why it's got formal semantics.
yeah, that's why it's formal. Right, but it gets less boring when you go through those terms and when you start explaining linguistic phenomena and you understand why, for example, English does double negation, cannot do double negation, and Italian does.
Okay. Saying that English can't do double negation is a bit of an overstatement. Let's be real here. But
Okay,
whatever.
I mean, okay, royal pronunciation, like royal English cannot. Yeah,
Standard English, sure.
standard English. All right. So, guys, I think we're going to the end. Those who still want to go on with this logical stuff, does exercises on page 63, 64, 65, and we'll continue with relations and functions next time. Okay?
Okay.
Now, is everyone's brains safe after that?
I can't wait to get to stuff where I'm not just explaining set theory.
Yeah, I see Ola's happy. Yeah? I guess this should be really, really easy for you because yeah, it's very close to math, and actually this is the demonstration where language and math intersect.
Say, write that out in set theory.
Yeah. And actually you saw this tree representation of semantics of the sentences meaning. And this is where syntax and semantics sort of meet each other. Of course, we can explain the word order with this tree-like manner, and we can explain the meaning, the semantics interface in this tree-like manner, and then we understand that Well, this is how we actually deal with those meanings in our brain. I mean, when we start speaking, we sort of join the smaller concepts into we using certain operations and relations and denotations. All right. This is the intersection. Thank you. Right. So yeah, I promise this is going to be less boring. But first, you need to, particularly those who are not good at math, we need to go through terms. And yeah, right. And then it's going to be more interesting.
All right, thank you very much.
Thank you for coming. Today we've got quite a group already.
Have a great evening.
Have a
Thank you very much.
good day, everyone, and see you next Friday.
Thank you.